In this module, we will try to understand why there was a need to build concurrency primitives in Go programming language. To understand that, we need some refresher on the concepts in operating systems, processes, and threads. The idea of concurrency comes from the operating system. The job of the operating system is to give fair chance to all the processes to run. Most of the time, it gives equal opportunity to all the processes, and there are times when a higher priority task can take precedence. The idea of concurrency starts with processes, threads, and when we come to Go, we will see how Go implements concurrency. Let us see what is a process. A process is an instance of a running program. A process gives an environment for the program to execute. When the program is executed, the operating system creates a process and allocates memory in the virtual address space. The virtual address space will contain code segment, which is the compiled machine code. There is a data region which contains global variables. Heap segment is the one which is used for dynamic memory allocation, and stack is used for storing local variables of a function. Threads are the smallest unit of execution that a CPU accepts. Each process has at least one thread, that is the main thread. A process can have multiple threads, and threads share the same address space, and each thread has its own stack. Threads can run independent of each other. The operating system scheduler makes scheduling decisions at the thread level, not at the process level. Threads can run concurrently, with each thread taking turn on an individual core, or they can run in parallel, with each thread running at the same time on different cores. Let us see the thread states. When a process is created, the main thread is put into the ready queue. It is in the runnable state. Once the CPU is available, the thread starts to execute, and each thread is given a time slice. If that time slice expires, then the thread gets preempted and placed back onto the ready queue. If the thread gets blocked due to an I/O operation like read-write on disk or network operation or waiting for an event from other processes, then it is placed in the waiting queue until the I/O operation is complete. Once it is complete, it is placed back onto the ready queue. Now you may ask, can we divide our application into processes and threads and achieve concurrency? Yes, we can, but there are limitations. Context switching. Context switches are considered expensive. CPU has to spend time copying the context of the current executing thread into memory and restoring the context of the next chosen thread. And it does take thousands of CPU instructions to do context switching. And it is a wasted time as CPU is not running your application but doing context switching. In this diagram, you might see the context switching between the threads of the same process is relatively cheap compared to the context switching between the threads of different processes. So you may ask, can we scale the number of threads per process? Not much actually. If we scale the number of threads in a process too high, then we hit C10K problem. Let us see what is that. The scheduler allocates a time slice for each process to execute on CPU core. This time slice is equally divided among the threads. So if we define the scheduler period as 10 milliseconds and we have two threads, then each thread is going to get 5 milliseconds separately for execution. If we have 5 threads, then each thread is going to get 2 milliseconds to execute. But what if there are 1000 threads? Then each thread will get 10 microseconds. This would be bad as CPU will be spending more time in context switching than running the application. So to do any meaningful job, a thread needs at least a minimum of 2 milliseconds. If a minimum time for the thread is 2 milliseconds, and accordingly we set the scheduler period, then to execute 1000 threads, the scheduler will take 2 seconds. If there are 10,000 threads, then it will take 20 seconds to complete one cycle of the execution. Each thread will have to wait for 20 seconds for its next execution. So the application is going to become less responsive. So other issue is the stack size. The operating system gives a fixed stack size for each thread. The actual size depends on the hardware. On my machine, it is 8 MB. So if I have 8 GB of memory, then in theory, I can only create 1000 threads. So the fixed stack size limits the number of threads that we can create to the amount of memory we have. We have come to the end of this module. Let us summarize. We saw what is a process. A process is an instance of a running program, and it provides an environment for the program to execute. We saw what is a thread. A thread is the smallest unit of execution, and every process has at least one thread, and processes can have multiple threads, and all threads share the same address space. And we saw what are the limitations with threads. Fixed stack size. Fixed stack size limits the number of threads that we can create to the amount of memory we have. And C10K problem, as we scale the number of threads, the scheduler cycle is going to increase and the application can become less responsive. We are done for this module. See you in the next module.